Hello there, and welcome back. Over the course of this linear algebra series, we've been primarily focused on vectors, vector addition, and scalar multiplication of vectors, and the set of all vectors that satisfy those 10 requirements that we talked about a while ago, in particular closure under scalar multiplication, closure under vector addition, distributivity of scalars over vector addition, commutativity of vector addition, and so on. If it satisfied those properties, we called that structure be a vector space. But of course, there are several different sets coupled with operations plus and times, and you can represent these binary operations in so many ways that are more structured than vector spaces, and there are also other structures that have less structure than vector spaces even do. So what I want to talk about today is both basic and also more complex different algebraic structures for which you can sort of classify matrices and other structures within, and then of course you can consider the applications and the theory behind them, which is more appropriate for say an algebraic structures course. But in this video we're just going to talk about some structures, how to sort of define these structures, and how to sort of figure out what type of objects are within these different types of algebraic structures that we're going to define today. So, before we get started, I just want to give a formal definition of what a binary operation is. So, an operation, and we're just going to represent this by star to be an arbitrary operation. It could be plus, it could be times, it could be division, it could be anything. This is called a binary operation, emphasis on the word binary, such that, or we're going to call it a binary operation, if this operation star is a relation from the Cartesian product of one set with another set, and of course S1 and S2 need to be non-empty, to another set T. Now, some people usually assume that these sets S1, S2, and SNT are typically the same, but they need not be. But they do not need to be. So let's look at a few examples of binary operations of where, S1, S2, and T are the same set, and also an example of where these sets actually don't need to be the same. Technically, the flexibility is up to you on how you want to sort of define these operations. So the first example, let's assume that we have the vector 3, 2, which we know belongs to R2, and let's consider the binary operation star, which is also going to operate on another vector in R2. And let's define this operation to be equal to, let's assume we're going to define this to be equal to the R2 vector 3 plus 5 and 2 times 4. So we're going to add the first components of the vectors, and we're going to multiply the second components of the vectors. So of course that's going to be equal to the vector 8, 8, which is also an element of R2. So we clearly see that this is a binary operation from R2 cross R2 into R2. So S1 and S2 and T are all the same exact set. But you don't have to define operations this way. You could literally define them in several different ways. For example, let's assume we have the vector 1, 2, and 3, which belongs to the vector space R3. And let's consider another operation. Let's actually represent it with a different symbol. Let's use like a triangle. So 1, 2, 3 triangle with, say, 4, 5. So an operation with a vector in R2. And let's define this to be equal to, let's do, for example, 1 plus 4. So we're going to be adding the first and the first element of the first and second vector. And then let's do 1 plus 5. So we're going to do the first element added with the second element. And then we're going to do, for example, 2 plus 4, and let's do 3 plus 5. Right. So 2 plus 4 and 3 plus 5. So you could create arbitrary elements, say A1, A2, A3, and B1 and B2, and define the general rule if you want to. So if that's the definition rule, then we have 5, 6, 6, and 8 as our element, and that's of course a vector in R4. So here we have a binary operation triangle, which maps the Cartesian product of R3 with R2 into R4. Now, one can ask, well, what's the purpose of these binary operations? What type of properties do these binary operations have? That, of course, is up to you to investigate since you created that binary operation. But generally speaking, binary binary operations are just Cartesian products between two non-empty sets into another set. Now that we have the basic notions of binary operations down, let's introduce our first algebraic structure that we're going to explore. So a structure X, which is going to be a set coupled with a binary operation, which we're going to represent by star, is called a magma if that set S is closed under star. So what do we mean by closed in case you don't remember? So we're going to choose two arbitrary elements X and Y in our set X, and if that S is closed under that star operation, then regardless of the elements X and Y we have chosen, once we star those two elements, that must also be an S. If that is true, then we say that that set is closed under that binary operation. And we call the structure X, which is the pair of that set with that binary operation, is called a magma. So let's look at our first pedagogical example. Let's assume S is the set of two operations. Let's call these operations alpha and beta. And let's define the operation star between alpha and beta in the following way. Right? So let's assume that alpha star alpha is going to be equal to alpha. Let's just say alpha star beta is going to be equal to beta. Let's define beta star alpha to be equal to beta, and let's define beta star beta to be equal to alpha. Notice that regardless of the elements that we choose in the set alpha and beta, notice every element within this table belongs to that set S. So therefore x star y is going to be an element of S for every x, y that you could choose in this set. And we can clearly see that from this multiplication table. So if that's the case, that means S is closed under this operation star that we have defined. That means the structure S, which is the structure S coupled with star, is what we call a magma. Right? So there is our first structure and an example of it. Now let's turn to our linear algebra examples and let's see if we can define a magma with some special matrices. So let's define S to be equal to the set of 2 by 2 matrices such that the determinant of A is not equal to 0. So that is going to be our set S, and let star denote ordinary matrix addition. Right, so our ordinary 2 by 2 plus 2 by 2 addition. Okay, so is this a magma? So this is the set of all invertible 2 by 2 matrices. So is it a magma? So if we take any 2 by 2 invertible matrices and we add them together, will it also be an invertible matrix? Well, you should know that the answer is no. So for example, let X be the element in S 1, 0, 0, 1, which is obviously an S. And let's choose Y to be the element negative 1, 0, 0, minus 1, which is also an element of S. So why are they elements of S's? Because the determinants of each of these matrices are not equal to 0, hence they are invertible. And let's do the operation x star y between them. So that's going to be equal to, by definition, 1, 0, 0, 1 plus negative 1, 0, 0, minus 1. And by ordinary matrix addition, we know that's the matrix 0, 0, 0, 0, which has a determinant of, let's call it the determinant of x star y. X star y is equal to 0, because that's 0 times 0 minus 0 times 0. So that means this element, x star y, is not an element of S. And we've chosen two particular elements of S and show that it's not closed. Now, it's possible that we add two invertible matrices and we do get a 2 by 2 invertible matrix, but in order for it to be a magma, it must be true for all. And since we chose two examples and it's not closed under them, that means this structure, S star, is not a magma. So the set of 2 by 2 matrices under matrix addition, not a magma. And that's a very important set, but it doesn't even satisfy the basic structure. So of course we cannot really define a vector space, at least with these operations. All right, so that is our first operation, but of course, or structure. Let's define our second. So our second structure is going to be the following. So a structure X, which is going to be, again, a set S coupled with a binary operation star, is called a semigroup if X is firstly a magma and star is associative on S. So what do we mean by associative or associativity on S? So that means if we choose x, y, and z in S, then x star y and then star z must be equal to x star the result of y star z. And that has to be true for all x, y, z in S. So let's see if we can construct an example of something that is not a semigroup. So let's consider the set S, which is going to be the set of elements alpha, beta, and gamma. And let's define the operation star on these elements. Again, alpha, beta, gamma, alpha, beta, gamma. And let's define the binary operation this way. Let's assume alpha star alpha is going to be gamma. Let's do alpha and alpha there. Let's do alpha and alpha there. Let's do alpha, gamma, gamma, and let's do our lonely beta in the corner. So we clearly see that every element written in pink is clearly an element of S. So we see that S star is a magma. So since it is a magma, we can then consider whether this operation is associative on this set in order to see whether the structure S star is actually a semigroup. So what we need to do is we need to choose 3 arbitrary elements. I'm just going to pick, for example, gamma star alpha, and we want to see, is this equal to gamma star alpha? And you need to do this for every single permutation of 3 elements that could possibly be chosen from the set, including all 3 repeated, right? So there's quite a few things to test if this set is really, really large. So what is this going to be equal to? So this is one particular example. If it doesn't work, then it's not a semigroup, but if it does work, we have to show that it's true for all other permutations as well. So alpha star alpha is going to be equal to gamma according to this table, so that's going to be gamma star gamma, and gamma star gamma is going to be equal to beta. So if this set is truly associative, that means gamma star alpha should also be equal to beta as well. But gamma star alpha is going to be equal to alpha, and alpha star alpha is going to be equal to beta. And notice that since beta and gamma are not equal to each other, that means the set is not associative. So that means star is not associative on S. So that means S star is not an associative magma, which means that S star is not a semigroup. At least it's a magma, but it's not a semigroup, right? So you could have, for example, an associative set that is not a magma, and you could have any, for example, mixtures of these definitions, of course. But in this case, we have an example of a magma that is not equal to a semigroup. Now that we know what a magma is and also what a semigroup is, let's define the next structure in the hierarchy, which is called a monoid. So structure X, which is a structure with a set S and a binary operation star, is called a monoid if X is firstly a semigroup, i.e. it is closed under the binary operation star, and star is associative on S, and this next property, there exists this element E in S such that E star X and X star E are both equal to X, and that has to be true for all X in S. And this element E is usually referred to as an identity element for star, or for S under star. All right, so the existence of an identity element for this particular binary operation. So let's consider a set S. Now let's let S be the set of all 2 by 2 matrices such that the determinant of A is not equal to 0. And let's define star to be ordinary multiplication. Because we already know that if we choose star to be ordinary matrix addition, it's not even a semigroup and hence not going to be a monoid. But if we look at ordinary multiplication, which we haven't looked at yet, maybe this is a semigroup and then we can consider if it is a monoid or not. All right, so let's first off start off and see, is this indeed a magma? So property number 1. So let's just assume we choose an element in A or S. Let's choose that to be B, A. i.e. the determinant of A is not going to be equal to 0. And let's choose another element B, also in S, implying that the determinant of B is not equal to 0. So under ordinary multiplication, if we take these two matrices and multiply them together, is that also going to be an invertible matrix always? So if we consider the product of A and B, and we want to see if AB belongs to S, what is the determinant of AB? Well, by properties of a determinant, we know that the determinant of the product is equal to the product of the determinants, i.e. determinant of A times the determinant of B. So we know that the determinant of A cannot be 0, and the determinant of B cannot be 0. Therefore, the product cannot be equal to 0 as well. So that means that AB also belongs to S, or in particular A star B belongs to S. And that means S is, or S star, is a magma. So S star is a magma. All right. So what about semigroup? So property 2. So is ABC equal to ABC, where we're doing ordinary multiplication? So we know that this is true for all matrices. This is actually true for all matrices, and this is actually inherited from the associative property. Associative property of the set of real numbers, which is the entries that we typically take to be in these matrices, or you could choose the complex numbers. That's also an associative set as well. So as long as you're choosing elements that belong to R or belong to C, then the product of these matrices is always going to be associative. So since our set S is a subset of all 2x2 matrices, then that set is associative as well, and therefore S star is a semigroup. Now we look at the third property to see if this semigroup is indeed a monoid. So does there exist an identity element such that X star E equals E star X is equal to X for all X in S? So what we can do is we can first think about what matrix do we have to multiply a matrix by in order to get itself, and we should know that that matrix is going to be the identity matrix 1 0 0 and 1, because we know that A B C D times 1 0 0 1 is equal to A B C D, and also the reverse multiplication as well. So that means this E belongs to this set S, because this is obviously an invertible matrix. All right, because determinant of E does not equal to 0. And that means that S star is a monoid. So it's a very well-behaved set. Now let's consider the next structure in the sequence. Like, is there something better than a monoid? Indeed, yes. So a structure X, again, a set S coupled with a binary operation star, is what we call a group. If, first off, X is a, take a guess, monoid, and for all X in that set S, there exists another element, X star. It could be the same element, it could be X prime in S, such that X prime star X and X star X prime are both equal to the identity element E that we mentioned in property 3 for monoids. So what we call, if star is addition, for example, that would be the additive inverse. If it's multiplication, that for that star, that would be the multiplicative inverse. So if we consider the same exact example for the set S under ordinary multiplication, is that indeed a group? So let's assume that we choose a 2x2 invertible matrix in S such that the determinant of A does not equal to 0. In particular, let's assume that A is the matrix A, B, C, and D, i.e. AD minus BC does not equal to 0. So this is going to be our element A that we're choosing in our set, and we need to find another element that is sort of related to A such that when we multiply by this element x prime, we get the identity element E, which we've already identified to be the matrix 1, 0, 0, 1. So if this is A, what we're going to do is we're going to define A prime to be equal to dA minus B minus C times the scalar AD minus BC, which some people will identify as the inverse of that matrix. So one should be able to see that if we do, for example, A times A prime and A prime times A, we're always going to be given, as a result, the inverse, the identity matrix 1, 0, 0, 1. And sometimes, again, this is denoted by A inverse. Right? So since every element A has an associated matrix A prime, and this matrix obviously is belonging to S, because if this is not equal to 0, that's not equal to 0 as well. All right? That's a very easy proof. So, since we already showed that S star is a monoid, and every element has this additive inverse, or multiplicative inverse if you may under star, that means we have that S star is a group. Right? So that's very wonderful. So one could ask, well, is there something better than a group? Yes, it is. So the next structure that we're going to define is the following. So a structure X S star is an abelian group. So it's an abelian group if, firstly, X is a group and star is commutative on S. So what do we mean by commutative on S? So that means X star Y equals Y star X for all X, Y, and S. So let's see if our set of invertible matrices under multiplication is an abelian group, because we've already proven that it is indeed a group, but is it an abelian group? So let's assume we choose two matrices X and Y both belonging to S. So is X star Y equal to Y star X? That is, if we take two matrices A and B, is AB equal to BA, where A and B are both invertible matrices? You should realize that the answer to that should be no. So you should be able to construct a counterexample of two invertible matrices that do not commute under matrix multiplication. So for example, let X be equal to the matrix 1, 2, 3, 4, obviously an invertible matrix. Let's choose another matrix Y, which is going to be 5, 6, and 7, 8, obviously an element in S as well. So first you have to show, okay, well, what is X star Y? Well, X star Y, once you multiply that together, is going to be 19, 22, 43, and 50. And if we do Y star X, if this is an abelian group, these two should be equal. But you should be able to see that that's going to be 23, 34, 31, and 46, and these two obviously are not equal to each other. So, since matrix multiplication on the invertible 2 by 2 matrices is not commutable, it is a group, but we have that S star is not an abelian or a commutative group, right? So we were able to get at least 4 structures out of that set, but we weren't able to get the 5th, but that's okay. At least it got 4 of these characteristics. What I want to do now is introduce some very important sets that you probably are already familiar with. The first set is called the general linear group. The general linear group. And some people will abbreviate this as GLN on R. GLNR. And this is the set of all n by n matrices that are invertible. So one should be able to show in a similar way that this is a group. So that's just a generalization of our 2 by 2 set S that we actually showed was a group. But it is not abelian for n greater than or equal to 2. And one can say, well, why do I need to specify n greater than or equal to 2? Well, if n is equal to 1, then we know that A, which is a 1 by 1 matrix, we know that this set is isomorphic to the vector space R, right? Which is the set of real valued scalars. Right? Because we know that if x and y are real numbers, xy is equal to yx, where x and y are in R. So if this is a one by one matrix, it will be an abelian group, but for n bigger than or equal to 2, this is not going to be an abelian group. But it is a group. So let's consider another set, which is actually a little bit more restricted, and this is called the special linear group. So the special linear group, which is abbreviated by SLNR, so it's the real valued matrices. Again, this is going to be the set of all m by n matrices. Also invertible, but with a more restricted restriction. The determinant of A is equal to 1. So it's a subset of our orthonormal matrices. Obviously, if the determinant of is equal to 1, it's obviously not equal to 0. So we see that SL and R is a subset of GL and R, the general linear group. So that's okay. You should be able to show that SL and R is also a group. So if it is a subset of that set, and it is also a group, then we say that SLN, the special linear group, we say that SLNR is a subgroup of GLNR. Right? So those are two very special groups that you definitely should be familiar with, and you may want to sort of explore, is there any subsets of SLN that are, for example, abelian groups? And you should be able to give me maybe at least one or two. Now, there is one very important property that you should have already guessed. So all vector spaces V, where S is a set of vectors, for example, say Rn or Rm, and plus, where plus is vector addition, is, or are, since we're talking about all vector spaces, are groups. Actually, no, it's even more bigger than that. They're all abelian groups. Because keep in mind, we assume that one of the properties for vector addition is that it must be commutative. Therefore, all vector spaces are indeed commutative groups, i.e. abelian groups. So that's actually very nice. So throughout this practically entire linear algebra series, we're actually been working with an abelian groups or subsets thereof. So up to this point, we define magmas, semigroups, monoids, groups, and abelian groups. So one could ask, is there any structures that are higher in tier than an abelian group, for example? So before we get into another set of algebraic structures, let's just go over just some basic properties for a very special set. In particular, let's consider the set S of all n by n matrices with no restrictions on it at all. So one should be able to show that, for example, S plus is an abelian group where plus is ordinary matrix addition. So if it is an abelian group, you should be able to tell me what the additive identity element is. So you should be able to tell me that the additive identity for the n by n matrix is going to be equal to 0, 0, all the way down to 0, with a bunch of zeros everywhere else. Right? So that's going to be the additive identity matrix. Right? In addition, you should be able to prove that S star is a monoid, where star is ordinary matrix multiplication. Right? So what would be the multiplicative identity matrix for this set? So that would be the matrix 1, 1, all the way down to 1, with zeros everywhere else. I guess that would be easier to write that, because those look like 1s, right? Right, so that would be the multiplicative identity matrix. But keep in mind, it is a monoid. That is an abelian group. This structure here is not a group, right? Because there are some matrices that do not have a multiplicative identity. For example, the zero matrix. Right? So if it's not a group, it can't be an abelian group, and we already know multiplication isn't commutative anyway, so even if it were a group, it can't be an abelian group anyway, because we're considering all n by n matrices. But at the least, S plus is an abelian group, and S star is a monoid. Can we build an algebraic structure with S plus and star that at least satisfy those structures? And the answer, of course, is yes. So consider the structure X, which is a triple with a set S and two binary operations, plus and star. And let's assume that X, Y, and Z all belong to S, right? So same structures, same set. So there are two properties that we usually want to be obeyed when we have two binary operations, in particular how they interact with each other. In particular, x star y plus z should be equal to x star y plus x star z, and x plus y star z should be equal to x star z plus y star z. The first is called left distributivity, and the second is right distributivity of times over plus, right? Because we're distributing multiplication over addition, right? We're not distributing addition over multiplication. That would be other types of structures, right? So left distributivity and right distributivity. So our next structure that we want to define includes these things. So definition. Consider the structure X, which is a set with two binary operations plus and dot. And this is called a ring if 1. S plus is an abelian group. 2. S star is a monoid. And 3. Times is left and right distributive over plus in the set S. That is, multiplication is left and right distributive over addition for that set S. So if S plus is an abelian group, S star is a monoid, and times and plus sort of interact in this distributive way, then we say that this structure, S plus star, is a ring. So that means we have, for example, S, which is the set of all n by n matrices, coupled with matrix multiplication and matrix addition as they are classically defined. And sometimes people will represent this set as MNR, all the n by n matrices with zero coefficients. Then, in a sense, we have already proven that this is indeed a ring. Right? So that's lovely, right? So that's, one could ask, well, is that the highest structure you can get? But for example, M and R, I'll leave that for your exploration. Now, what about vector spaces? Are vector spaces rings? Well, let's sort of think about that for a moment. So, question, are vector spaces rings? Well, let's consider what a vector space is. Well, usually a vector space V is a set S with two binary operations plus vector addition and times scalar multiplication. Let's consider the distributivity property for a minute. So for example, if we have X star Y plus Z, where dot is scalar multiplication and plus is vector addition. Well, if that works, maybe it is, maybe it is not, right? Because obviously scalars distribute over vector addition moreover. But what if we define that as, for example, a dot product? If times is a dot product, Does that also work, right? Because if we take that to be a dot product, well, we know that that is going to be a vector, but the dot product of x with a vector, that's going to be a scalar, not a vector, right? And keep in mind those operations must be in S, right? So if we define that as the dot product, it definitely doesn't work. If we define it as scalar multiplication, maybe it works, but keep in mind, what about scalar multiplication would cause this to not work? For example, if S is a set of vectors in Rn and times is scalar multiplication, does this really work? So for example, if we have, for example, a vector x scalared with y, well, this can't really be scalar multiplication because x would be a vector and y would be a vector, and we can't scale a vector by a vector, at least not in the classical sense anyway, right? So generally speaking, vector spaces are not rings if we define plus as vector addition and times as scalar multiplication. In order to construct a ring out of a vector space, well, we already know that S plus would already be an abelian group. Then you just need to define another operation star that would at least be a monoid with S. And then hopefully the distributive properties between times and plus would interact with each other. So what I want to do is actually build a ring via a clever definition of star. Right, so let's start off with the basics. So let's assume V is the set S plus be a vector space with S being the set of all vectors in, let's choose R2, but you could extend this to Rn if you really want to. And let's assume plus is normal vector addition. All right, so we already know that if this is a vector space, then we know that V is an abelian group. So that's not a concern. So now we need to create a new operation, star. So let's consider S star. Again, S is going to be an R2, where S with the star is element-wise multiplication. So what do I mean by element-wise multiplication? So if you're familiar with MATLAB, this would be the dot star operator. So if we take an element in R2, so let's call it x1, x2, and we start with y1 and y2, and some people actually want to treat multiplication between vectors in this way, but we're going to be defining this as the product of x1 and x2, or x1 and y1, and x2 and y2. So obviously that's going to be an R2 vector. Obviously it is a magma. So this is a magma. So S star is a magma. And since we have multiplication of real numbers on the right-hand side, it is also a semigroup. So the next thing we need to figure out is, okay, under this operation of star, is it a monoid? Well, if it is a monoid, then we need to answer the question, what is the identity element, E? Right? So in particular, x star E must be equal to E star x, must be equal to x for all x in our set R2. So what vector in R2 do you think this is? Well, if you're clever enough, you should know that x1, 2 starred with the vector 1, 1. This is also equal to the vector 1, 1 star x1, x2, and that's going to be the vector x1, x2, and that's actually easy to prove because x1 times 1 is x1, and x2 times 1 is also x2. Right? So this is going to be our identity element E, which is obviously an element of R2. Therefore, we have identified that this structure, S star, is indeed a monoid. And if our goal is to just have that S plus star is a ring, the only structure hierarchy that we need for S star is a monoid. We do not need this to be a group, and we do not need this to be an abelian group. And you can investigate those on your own and see, is this indeed a group? Is this indeed a abelian group? And so on. Right? So if we extend this, is this a ring? Then obviously we have to check, does it satisfy those properties of left and right distribution? So x star y plus z. So what's this going to be equal to? So this is going to be equal to x1, x2 starred with the sum of y and z, which I'm just going to call y1 plus z1 and y2 plus z2. And element y's multiplication, this is going to be equal to x1 y1 plus x1 z1 as we've defined it, because it's element-wise. We're just multiplying that by that and that by that. So this is just going to be x2, y2 plus x2, z2. And since we know the set of scalars is abelian, then we know that this is also going to be equal to, for example, y plus z starred with x. So it's actually equal to what they actually should be equal to. In particular, x star y plus x star z, and also y star x and z star x. So these are both going to be true, so it satisfies the left and right distributivity properties of star and plus. So since we have that S plus is an abelian group, we have S star is a monoid, we then have that S plus star is a ring. Right? Now, one can ask again, are there more higher structures? Are there more complicated structures? Can you couple this with, for example, two sets? Can you throw a third binary operation? Do they have to be binary operations? Can you do like unary operations? What if you impose an ordering on this set? What if you do like, for example, tertiary operations on this set? What if you start picking apart pieces and adding new properties for which you want? For example, you want, for example, A plus B plus C to be equal to A plus B times C, like you call that the whatever-tivity property of the set. Of course, you can define these sets and you can investigate the properties, but again, that's more of an algebraic structures related discussion, which we will definitely have in the future. But until then, I hope you enjoyed this video. Take care.